What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of evaluating the 3D awareness of visual foundation models. Specifically, it aims to understand how well these models represent the 3D geometry of scenes and objects by assessing their ability to encode basic 3D properties such as depth, surface normals, and multiview consistency. The method focuses on probing the frozen representations of large-scale pre-trained models using task-specific probes and zero-shot inference methods to evaluate their 3D understanding without fine-tuning the models. By conducting empirical analyses on a range of models trained with different supervisory signals, the method aims to provide insights into the 3D awareness of visual models and contribute to more comprehensive benchmarks of visual representation learning approaches.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method in the paper works by evaluating the 3D awareness of visual foundation models through two distinct capabilities: single-view surface reconstruction and multiview consistency. Firstly, the models are probed using trainable probes and zero-shot inference methods to assess their frozen representations without altering the model weight significantly. This allows for the evaluation of how well the models encode the geometry of the visible surfaces, including depth and surface orientation. The models are then tested for consistency across different views of the same object or scene to determine if they can establish accurate correspondence between multiple images. The evaluation is done using correspondence estimation, where the goal is to identify image patches across views that depict the same 3D point. This process involves computing correspondence between dense feature maps extracted from each image to directly assess the consistency of the representations. The performance is evaluated on both scenes and objects datasets, considering factors like viewpoint differences and rotation angles to ensure accurate assessment. The method aims to understand if the models can capture 3D properties and maintain consistency across different views, providing insights into the model's 3D awareness capabilities.
What are the theoretical or practical benefits of using this method?
The theoretical benefit of using the method described in the paper is that it allows for the evaluation of visual foundation models' 3D awareness by probing their representations on two key capabilities: single-view surface reconstruction and multiview consistency. This method helps in understanding how well the models encode the geometry of visible surfaces and how consistent their representations are across different views. By evaluating these aspects, researchers can gain insights into the model's ability to understand the 3D structure of scenes and objects, which is crucial for various computer vision tasks. Practically, this method provides a systematic way to assess the 3D awareness of visual models without the need for fine-tuning, thus preserving the generality of the pre-trained models. It allows for a direct evaluation of the frozen features of the models through trainable probes and zero-shot inference methods, providing a deeper understanding of the representations learned by the models. This approach can help in identifying strengths and weaknesses of different models in terms of their 3D understanding capabilities, which can guide future research in developing more robust and accurate visual models for tasks such as depth estimation, surface normal prediction, and correspondence estimation across multiple views.
How is the method validated or tested?
The method is validated or tested through an empirical analysis of the 3D awareness of visual foundation models. The analysis considers a range of large-scale pre-trained models that have shown strong generalization capabilities. The models are evaluated on their ability to estimate 3D quantities such as depth, surface normals, and 3D correspondence at both the scene level and for individual objects. The frozen representations of the models are probed using task-specific probes or zero-shot inference methods to evaluate the model's representations without fine-tuning. The experiments reveal a wide variation in the 3D awareness of the models, with some models like DINOV2 and Stable Diffusion performing well in encoding depth and surface normals, while others like CLIP showing poor performance. The models are further evaluated on single-image surface reconstruction tasks, such as depth estimation and surface normal estimation, using dense multiscale probes and optimization techniques. The performance of the models is assessed on datasets like NYUV2 for scenes and NAVI for objects, with results reported in detail in the paper. The method is validated by analyzing the model's performance in accurately representing depth, surface normals, and correspondence across different tasks and domains, providing insights into the 3D awareness of visual models.
What results were achieved with this new method?
The new method achieved results that showed visual foundation models, such as DINOV2 and Stable Diffusion, were able to encode depth and surface normals accurately. These models exhibited strong performance in estimating 3D quantities like depth and surface normals, with DINOV2 performing competitively with state-of-the-art models. However, the models struggled with multi-view consistency, especially with large viewpoint variations. The analysis revealed that while models could accurately match objects and scenes with small viewpoint changes, they performed poorly with significant viewpoint variations. The study also found that discriminative self-supervised models performed the best across tasks and domains, while models trained with dense supervision, including depth estimation, performed worse. Additionally, language-supervised models showed poor performance in representing 3D properties. The results indicated that most visual foundation models learned representations that encoded properties of the visual surface, despite being trained solely on image data.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the following. 1. Heterogeneity in pre-trained models. The study used pre-trained checkpoints that were trained on different datasets and with varying compute scales, making it challenging to make targeted and fair comparisons to understand the impact of training signals. 2. Minimal probing approaches. The analysis focused on minimal probing techniques to analyze the pre-trained representations, leaving uncertainty about the most effective method to comprehend the distributed representations learned by visual models. 3. Limited scope of analysis. The study only explored two fundamental aspects of 3D understanding, depth estimation, and multi-view consistency, while more complex tasks like perceiving 3D shapes, reasoning about spatial relationships, and predicting deformation and dynamics were not addressed. 4. View-dependent representations. The models may be learning view-dependent representations, similar to theories of shape perception where shape understanding is achieved through a series of view-specific representations connected with an aspect graph, potentially limiting their 3D consistency. 5. Lack of comprehensive understanding. While the models demonstrated the ability to encode depth and orientation of visible surfaces, there was a struggle with large viewpoint changes, indicating a deficiency in multi-view consistency and suggesting that the models may be learning view-consistent rather than 3D-consistent representations. 6. Need for further exploration. The study acknowledges the need for more targeted comparisons, exploration of diverse probing techniques, and investigation into higher-order 3D tasks beyond basic depth estimation and multi-view consistency to gain a more comprehensive understanding of 3D awareness in visual models. 7. Uncertainty in representations. It remains unclear whether the strong performance in 5D understanding achieved by the models is due to them being good image models with discriminative features, raising questions about the depth of their 3D understanding. In conclusion, while the study provides valuable insights into the 3D awareness of visual models, there are limitations in terms of model heterogeneity, probing approaches, scope of analysis, potential view-dependent representations, and the need for further exploration into more complex 3D tasks.
What future work do the authors suggest?
The authors suggest that future work should delve deeper into understanding the 3D awareness of visual models by exploring more complex and higher-order tasks related to 3D understanding. They propose investigating tasks such as perceiving 3D shapes, reasoning about spatial relationships, and making predictions about deformation and dynamics. The authors acknowledge that their current analysis only scratched the surface of 3D awareness and understanding in visual models. They highlight the need to explore additional probing techniques beyond the minimal approaches used in their study to gain a better understanding of the distributed representations learned by visual models. Furthermore, they emphasize the importance of making more targeted and fair comparisons by using pre-trained checkpoints trained on similar datasets and compute scales to better understand the impact of different training signals on 3D awareness. The authors also encourage further research into whether current models are learning view-dependent representations or if good discriminative features are sufficient for strong 5D understanding. They hope that their findings will spark more interest in investigating how visual models represent the world in terms of 3D structure and how different learning objectives impact these representations.